language that makes the two of them a lot closer and makes translation easier. So we enable that extension for all of our shaders. HLSL allows C-style casts, GLSL does not, so we just convert that to constructor syntax, and that works in both languages. HLSL allows you to have conditionals that are just tests on an integer, whereas GLSL requires Boolean expressions, so we just always write Boolean expressions. And HLSL allows static local variables, and GLSL does not, so we just don't use them. Now, all of these rules, as I said, are part of our coding standard, but also during validation, at compile time, we check that our code is compatible with GLSL. So it's very much an integrated part of our development now, where our developers are authoring shaders, they'll know right away whether their shader's compatible with GLSL. Some other things we do is that we use the STD140 layout qualifier on uniform buffers. And this basically defines a set of rules around how types are packed into uniform buffers. And what we do on the HLSL side is we actually generate pack offset qualifiers on the constant buffers that exactly match the STD140 rules. And what this means is that our layout in memory for uniform or constant buffers in the D3D parlance are identical. And our engine doesn't need to care about whether it's running on D3D or GL. The in-memory layout of constant buffers is always the same. As Jason mentioned, we use separate shader objects, which allows us to compile and link each shader stage independently, much like D3D does. And we use this shading language 420 pack extension. The final thing I wanted to talk about with translation is the shader reparser. So as I mentioned, we had this goal that we wanted to avoid doing any runtime reflection. We didn't want to worry about the fact that when you compile and link a shader, each implementation of OpenGL will assign uniforms and uniform buffers to its own implementation-dependent locations. We wanted our shaders to be able to be baked in as a preprocess and not have to do this at runtime. And this is the same thing we do at D3D. So the way we do this is that after we've done our translation and have the original GLSL, we validate it to make sure it's syntactically correct. And then we perform reflection on the shader where we query for all of the active uniform buffers and samplers. And then what we do is we go through and we insert binding qualifiers on the uniform buffers. So this would basically say that this per view constant buffer is bound to a particular uniform buffer binding. And we do the similar thing with samplers, where for all of our active samplers, we'll insert a binding qualifier that binds it at compile time to a texture unit. After we've done this reparsing, we validate it again, and then we have our final GLSL. So the key point here is that by inserting these binding qualifiers, we are able to avoid doing any reflection at runtime, and our preprocess tool knows the location of samplers, what texture unit they're going to be bound to, and what uniform buffer location the uniform buffers will be on. So I've talked so far about how we translate from HLSL to GLSL. I want to talk now about how we validate that our GLSL is correct. So the problem is, you know, if you're writing GLSL, for those of you who have, you know that each OpenGL driver has its own compiler. And this can mean you can run into bugs where your shader works on one driver but not on another. In D3D, you don't have this problem because you can use FXC or D3DX to find out offline whether your shader is correct. So basically, the problem is OpenGL compilation is tied to what hardware you have and what driver you have. We wanted to be able to know whether our shader conformed to the OpenGL specification across all implementations. So one idea we had was, hey, maybe we could just compile our shaders on every driver that's available. And we actually went down the route of exploring this, where we have a distributed compilation tool, and we modified it so that it could go out on our network and find, say, all the machines that have a particular NVIDIA GPU with a particular driver or AMD GPU with a particular driver. But this was just incredibly painful. For one thing, our distributed tool that does this uses our own internal development machines, and keeping everyone up to date with drivers was just a nightmare, and also hitting all hardware combinations just was too painful. We thought about using CGC, which is NVIDIA's tool that can take GLSL or CG as input, and well, it compiles it and can produce HLSL, GLSL, or GL assembly as output. The problem we had with this tool is that, first of all, NVIDIA pretty much end-of-lifed it in April 2012. It hasn't been updated since then. Also, it really only tells you whether your shader is correct for NVIDIA because it basically contains their compiler infrastructure. We took a pretty close look at Mesa's parser, and we thought about using that, and it actually looked like a really good option, although at the time we were evaluating it, it was a little behind the shader features that we intended to use, but we were thinking about using that. However, as we thought about this problem some more, we realized that this is not just a problem for Valve, but basically anyone who's developing OpenGL using shaders. And we came to believe that the right thing is that OpenGL should have a reference implementation. You should be able to find out offline, is your shader conformant with the spec? And we went around and discussed this with other ISVs and within Khronos. And thankfully, Khronos came through and selected Slang as a reference implementation. So I'm going to talk now about what Slang is and how we use it. So Slang is an open source tool. A bit of history about it is that in the early days of OpenGL 2.0, 3D Labs produced a GLSL parser based on Lex and Yak, and they open sourced it. And 3D Labs subsequently went out of business, and some of the people who were there are now at LunarG, and they've basically rewritten this parser and extended it for modern OpenGL. It's open sourced under the modified BSD license, which is very liberal. It has a C and C++ API, so you can access it programmatically. It also has a command line tool, and it's currently available on Linux and Windows. It's pretty vanilla code, so I'm sure you could easily compile it for macOS as well if you tried. I haven't tried myself, but it should be simple. Valve actually worked very closely with LunarG and actually funded some enhancements to Slang to make sure it could support all of the features that we needed. Namely, support GLSL 4.2, support geometry, tessellation, shaders, the 420 pack extension that I mentioned, as well as GPU Shader 5. It basically supports all of that. There's some small corner cases where it doesn't yet, but it's very close. We also worked with LunarG to develop a reflection API. As I mentioned earlier, the idea was we wanted, as a pre-process, to be able to find out what the active uniforms and uniform buffers were in our shaders. So we worked with them to develop an API that's implemented in Slang, so you can find out that information about your shaders. So the way we use Slang in Source 2 is that basically every shader we have is validated and reflected using the tool.